Good afternoon. I'm Arun Serafin, Executive Director of the Emerging Technologies Institute at the National Defense Industrial Association. I want to thank all attendees for your support of NDIA and ETI and for joining us for today's webinar, Resilient Materials 101 with Dr. Gary Haleda. This webinar is part of our Tech 101 series, where we present complex technological concepts as introductory webinars with a focus on their national security implications. Resilient materials are materials designed to endure and recover from extreme environments and stress, and they're proving essential to ensuring the reliability and survivability of military systems and personnel in contested and unpredictable environments. Resilient materials are becoming a strategic priority as defense operations are always facing harsh conditions. Think Arctic or undersea or space, and evolving threats and increasing demands for durability and adaptability, all at lower costs. This introductory webinar will examine the fundamentals of resilient materials, explore key categories and defense use cases, and highlight their expanding role in enhancing system survivability, reducing maintenance burdens, and supporting long-term operational effectiveness. Now, some administrative items before we get started. All attendee lines are muted. If you have a question during the webinar, you can submit it in the Q&A box in the webinar panel. We will do our best to get through all the questions during the Q&A portion of our session. We're recording today's webinar for members unable to attend, and we'll post that recording and the slides on our YouTube channel and our website. Now to introduce our speaker, Gary Haleda is an associate professor and director of the Engineering Science undergraduate degree program in the Department of Material Science and Chemical Engineering at NDIA member university, Stony Brook University. For more than 20 years, he's led research projects funded by the National Science Foundation, the Department of Energy, and private industry. His projects have included work on nanomaterials, environmental cleanup, green technologies, and the design of advanced materials for a variety of commercial and defense applications. His research has resulted in over 100 peer-reviewed publications. Gary, thanks for joining us today. For the use of these materials, we're going to need an understanding of their basic properties and their uses and their limitations, honestly. And as they say, to do, one must first imagine. So help us imagine the possibilities of resilient materials. Gary?
Thank you very much. Thanks for the great introduction, and happy to see, happy to be able to speak to everybody here. I apologize, I'm not wearing my own jacket and tie, but my air conditioning is down in my office. It's down to all of 92 right now. So if I pass out, just speak amongst yourselves. It's fine. Anyway, let me. I think you should be able to see my slides, if that's correct. And so let me just, whoops. Okay, that's better. So again, I'm Gary Haleda. I'm in the Department of Material Science and Chemical Engineering. If you note my email address on there.
Hey, Gary, you're not sharing yet.
Oh, I'm not? Oh, shoot. I thought I was. It looked like I was. Oh, I hit the wrong thing. Now I'm sharing. Hi, here I am again. So if you know, okay, if you note in the first slide, you can see my email address down there, gary.haleda@stonybrook.edu. So if you have any questions beyond this, and honestly, I probably have too many slides. So so there may become maybe things I don't have a chance to talk about, things that questions you have. I know we're gonna have a question and answer session at the end of the talk today, but just in case, please feel free to just drop me a line anytime. Okay. So oops. Get this going. So what I want, as Arun said, this is really kind of a basic look at resilient materials. I can't talk about all resilient materials, but I can talk about what factors are important and give some ideas, some thoughts, some case studies, some examples. And some of the slides will be kind of high-techy stuff, but we'll just look at some important factors about them and things that you may find useful as you think about your own thoughts about needs and materials that may be out there or could be developed, and how those materials are developed. So we'll talk about how materials fail a little bit, not extensively. We don't have time, but we'll look at some physical and chemical mechanisms that lead to failure. And then we'll talk a little bit about what the key characteristics of materials and material systems, which are sort of combinations of multiple materials and material structures that are needed for resilience or robustness. And we'll look at some examples of tough, robust, and resilient materials, often the same thing. So let me just. So how materials fail is a complex question. I've spent, a large part of my academic research career, as have many of my colleagues, studying failure mechanisms. And essentially, a lot of the ones that you're concerned about that occur under extreme conditions are either some form of mechanical failure, like cracking. That's a technical term, cracking, or sometimes just fracture, and also chemical attack, for example, corrosion, or chemical degradation, which can occur under a lot of different conditions. And there's a lot of threat multipliers that make these things more likely to happen. For example, very high temperatures, very low temperatures, and sometimes the most dangerous of all is a combination of mechanical failure and weathering or corrosion. An example you see at the bottom of the screen there is a stress corrosion cracking caused failure. This was Flight 243 of Aloha Airlines in 1988 in Hawaii. And yes, you see what that very much looks like a jumbo jet that turned into a convertible. And basically what happens is you have a corrosive environment. We're talking about flying between the Hawaiian Islands and the mainland, a lot of salt water, a lot of humidity. That starts corrosion, and the corrosion accelerates where you have stresses in the material. If you want to see an example of this yourself, take a piece of metal, any piece of metal that is likely to corrode, put it in the water, especially salt water, and then take the same material and bend it in the middle, and then straighten it out, or just leave it bent, it doesn't matter, and put that in the salt water. And you'll see that corrosion starts to occur rapidly where you have the bend. And this is really because that's where you have extra energy added to the material. A lot of what we'll talk about with resilient material is how to absorb energy, how to redirect it, because all mechanical uses of material, generate energy in the material itself, generate stresses and forces. Those stresses can lead to conditions where, for example, corrosion is more likely, or other failure mechanisms. So I'm not going to, again, this is a very high-level, light talk on these things, but there are other failure mechanisms besides mechanical and chemical degradation failure, which I won't talk about too much here. For example, failure due to various radiation, electromagnetic radiation, and heat is, of course, a form of this in a sense, because normally we're talking about heat being generated as a byproduct of electromagnetic radiation, but that's sort of infrared light. UV light, or high energy light, can also cause damage. You think about, for example, what can happen to your skin under UV light, why you would wear a sunblock, because UV light is very active in causing damage, especially if you have other conditions present, for example, humidity or something like that, because a combination of water and UV light can, especially wet dry cycles, can lead to very rapid damage, especially to polymeric materials, the plastics, and to some metals too, even if they have certain chemicals on the surface. When we saw this with, we were seeing damage to copper-based alloys just because they had been cleaned with acetone before exposure to light and humidity. And the acetone resulted in the formation of copper acetates, and that process was accelerated by light. So it's interesting how these effects combine together. And of course, ionizing radiation. One area that you might be concerned with are materials for say, nuclear reactors or environments like that. And especially with next generation nuclear reactors and fusion systems on the horizon, this is a source of a lot of research going on right now. Just as an example, things that can happen. You can get something called you get radiation hardening and embrittlement. You'll due to the chemical reactions induced by the radiation. And this is ionizing radiation, something you might get in a nuclear facility. You get changes in phases, little precipitates that form in the material, a lot of defect structures that form from radiation that can accelerate creep. Creep is a form of mechanical failure. That's where if you hang a heavy weight from say a lead bar, that weight will slowly lengthen the bar, and the bar will get narrower, and eventually it'll break. And that's what's happening is a process of creep where atoms are moving past each other in the crystalline metal materials. You can also get the formation of voids because you get gas generation from irradiation of certain materials, and so forth. There's and you can see that, for example, this was looking at irradiation damage in tungsten. Tungsten's a really good material for a lot of applications, a very strong material, a very durable material. However, under high temperatures and irradiation, you can see the formation of voids that become larger with time in the material, which can lead to failure. So you're going to see increased porosity, even in something that you would not expect to see it in, for example, a piece of tungsten metal. So there's a lot of conditions that can lead to failure. A lot of what, for example, what happened, one of the materials that have been developed for high radiation environments are nanocrystalline materials. And a lot of metals, metals are crystalline materials. And the crystal structures in materials are in the order of usually maybe 100 microns or more, maybe 50 to 100 microns in size for these crystals. And then all the crystals are packed together. And that's what a solid material looks like. However, a nanocrystalline material has been treated so the crystals are very small. Now, why that's important is that a lot of the defects that are formed due to radiation can actually move to grain boundaries, which are the spaces between crystals. And if it's nanocrystalline, you have a whole lot of these grain boundaries, and these little defects can get eliminated or stuck there. And in fact, we're doing a lot of work on that at Stony Brook. I'm just mentioning there's a paper at the bottom, which I'm not going to show you data from because I looked at it, but it's a little bit too complex. But Dave Sprouster and Jason Cholowitz and Lance Sneed are some of our faculty here. And they're looking at sintered nanocrystalline stainless steel for nuclear reactor applications in the engineered microstructures and radiation effects lab. So it's a very exciting new area of research to look at metallic glasses, and glasses are essentially nanocrystalline material or just nanocrystalline alloys in general. Now, this idea of having these boundaries or separations in a material, places where atomic structure changes for one reason or another, that's not a new idea. That's been around since, well, forever. A few quick examples of that, if you ever know, I'm sorry, these are kind of blurry, but how, for example, if I don't have a pointer on my thing here, but that's okay. I don't need a pointer. I can just tell you what I'm looking at. Oh, there it is. I found my pointer, I think. Let me just make sure all right, for example, this top picture on the left, this is, for example, a samurai sword. That's made since ancient medieval times. In Japan, for example, one of the ways that you can't read it, it's too blurry, but one of the reasons why it's such a robust material, or it's such a robust sword, is that the metal is made in thin layers that are folded together many times, hundreds of times. And the thing is, when you fold the metal over, you form boundaries between layers of the metal. So if a crack starts to form, which is a type of defect in the material, it actually hits the interfaces. The same thing can be said of other metals that have been very famous for their use in swords. For example, Damascus steel, more properly called wood steel. In the upper right here, you see these swords that were made, in the East, and these swords originally actually developed in India, had a microstructure that included these lines of carbide particles. Those carbide particle patterns, which could be quite beautiful on the surface of the metal here, on the surface of the steel that was used, were formed due to adding phosphate to the steel. And actually, the phosphate and other materials and calcium that enable these small particles to form came from putting bones into the furnaces, so that you would add those materials to the metal. So it was kind of considered magical at the time, but we now know how it works. And again, a crack, which is a defect, hits particles and gets stuck. And so it becomes a more robust material. And even Western medieval sword making, for example, like in this bottom picture in say in Europe, involved the process of hammering, which induced some defects in the steel, but also they would anneal the steel, they'd heat it to a fairly high temperature in a furnace, and then they would put it into a cooling medium, not necessarily water. Oftentimes they would put it into oil, or even sometimes they put the sword through an animal just to slowly cool it, because that would freeze in, again, a microcarbide structure that prevented cracks from traveling through the material. So this idea of building grain boundaries in a piece of steel so you can use it in a nuclear reactor is actually based on really old ideas, as a lot of these are. Let me move on. Another thing about whether it's radiation-induced damage or other damage, usually damage evolves over time, and it often grows from microscopic size. This is you don't need to worry about what this chart is all about. This is really about damage from neutron irradiation in materials. And in this paper, they were looking at all the different techniques they use to analyze it, which we don't have time to get into here. But the idea is that you go from very small nanoscale damage up to millimeter and larger scale damage over the course of time, over the course of exposure to radiation. And so this idea of growing damage is really important. It's really at the basis, for example, of fracture mechanics. Cracks that form in a material are a response to stress. You know this for yourself if you've ever had a tiny crack in the corner of your windshield, and it just sits there. And in the winter, say, and you put the heat on your car and it's cold outside, and you go through these cycles of heat and cold. These thermal cycles put tremendous stress into your windshield. The way the windshield relieves the stress is by forming new surfaces of material. It forms a crack, and that crack starts to get larger and larger. And as you may or may not have had the experience of in your life, a tiny crack at the corner of the windshield, one day you'll get in your car and you'll see the crack is going straight across the windshield. And that's the point at which you have to get the windshield replaced. But anyway, and they actually try to stop this from happening by drilling little holes at the crack tip or doing something like that. And this is due to a fracture mechanics basic concept known as critical crack length formation. In that process, you basically have a balance between the energy required to form new surfaces and the energy that's released by the formation of a crack. And when these two balance out, you or get to a point of maximum energy, that's called at a certain length of crack, because it's based on the length of the crack. This is called the critical crack length. Once you get past this, the crack forms spontaneously. It's a very famous example in World War II, which you may or may not have heard of, called Liberty ships. At the very end of World War II, we had to get a lot of troops to Europe very, very quickly. And so the normal process of making ships involved using rivets and holding metal panels together with rivets. They wanted to make these ships very fast, so they used welding. The problem with welding, or one of the problems, is that there's no give in the material. You can't bend it. You can't, because usually when there's rivets, everything can shift a little bit. That's a good way of absorbing energy. If you can't absorb the energy that way, you can absorb the energy by forming a crack. There's a very famous example of a cook on one of these Liberty ships who was traveling across the Atlantic who noticed a crack in the floor of his galley. And he went to the captain and said, I got this crack here. I'm worried about it. And the captain didn't want to hear about it because the crack was small, and said, well, tell you what, why don't you put a little mark at the tip of the crack? And that way we can see how fast it's growing. I wanted to kind of get the cook off his back. And then, we'll get to it when we get to port. We'll have somebody look at it. Well, they knew exactly how long the critical crack length was, because when they found the two halves of the Liberty ship at the bottom of the ocean, they could see the exact marks that the cook made on the floor and the point at which the crack moved spontaneously and essentially sank the ship. So I love these old nautical examples too. We can also talk about how different conditions can make materials more brittle. For example, as materials become more brittle, they're more likely to fail by cracking because the critical crack length ends up being very small, and so they don't, they lose their flexibility. One of the most famous historical examples was of course the Titanic that sank in 1912. In that case, and they've done some research on this, what happened at the Harland and Wolff shipyard is they were in a big hurry to build 3 ships all at once, 3 giant ships, and so they were supposed to be using a type of steel called A36, which you see down here. And this shows the difference in impact, the relationship between impact energy and temperature. So as you're looking at a freezing temperature, as you see here, you can see the impact strength has dropped a lot. Now, the Titanic had an impact incident. It was a big thing called a iceberg. And when it hit it, the whole side of the ship unzipped because the rivets that were used were not A36 steel. They were a much weaker form of steel because they were in a hurry. That steel was much, much weaker, especially at freezing temperatures. So yeah, this is a replica of one of the rivets, and it's actually made of A36 steel, and this is what should have been used, but instead they used a much weaker steel that they were in a hurry to complete their work with. So again, this was a problem not just of material failure, but also haste, right? Okay, so what are some of the key properties for resilience? Probably the most important one is toughness, if we're talking about mechanical resilience. And you can think about the comparison, for example, between the mighty oak tree, right? An oak tree is very, very strong, one of the strongest woods. And under most conditions, that will be very durable, right? If you compare that, for example, to a palm tree is not as strong. It's not going to hold as much weight up at the top. If you were to go build your tree house in a palm tree, it might start bending all the way over because it's not that strong. But there's something about the wood of the palm tree and the structure within that wood that make it somewhat flexible. This is really key to toughness, because if you have a hurricane, for example, an oak tree will snap. A lot of trees will snap. They don't bend, they snap. Very strong, but not very tough. A palm tree can actually bend all the way to the ground and snap back up again. That is a tough material. So that's kind of what you want to look for in materials that you want great resiliency for. You want a good balance between toughness and strength for mechanical resiliency. This is something called a stress strain curve. And it shows that materials that are very high in strength but have low ductility have low toughness. And materials that have low strength and high ductility also have low toughness. The reason for that is that toughness, it relates to the area under the curve. The area under the curve is the energy that's absorbed before breaking. So the more area under this curve, the more energy the material can absorb. This is something that's been exploited in new materials developed by those fantastic scientists at Marvel Comics. For example, think about Captain America's shield or the armored clothing worn by Black Panther. These were both made of something called vibranium. I love these, unobtainium, vibranium, things like that. But the key factor in these materials, as described in the comics and the movies, is that they absorb energy and then sometimes re-release it for its own purposes. But the idea is that it's very possible these are made of nanostructured metals, for example. But they don't really explain what vibranium is, except I think it came from a meteor or something. I forgot. In comparison to the adamantium, the other big material discussed in Marvel Comics, which is in the claws of Wolverine, and that's just really, really strong. It's not really, really tough. So I don't know how they would do against each other, but maybe we'll see sometime. Anyway, resilience often involves this idea of absorbing energy. So, for example, if you've ever been in Arizona, there's a wonderful museum in southern Arizona, the Titan Missile Museum, where they actually have preserved and no warhead included, no fuel included Titan missile in its bunker, in its where it's fired from. But they also have all these structures underground that you can go and visit, the control room and so forth. And what's critical in these kind of facilities is the survivability of these underground structures in case of a direct hit or a nearby hit, where it puts a lot of vibration in the ground. So what do you do to try to stop these structures from being damaged so that the people in them can fire the missile back, is basically putting giant shock absorbers in that actually hold up the floors inside these buildings. I had a chance to walk around and look at these. They're very interesting. If you're in Arizona, go visit the Titan Missile Museum. It's really interesting. But they have these basically almost like car shock absorbers, that absorb the energy, the vibrations, and those can be then those don't result in damage. There's similar structures, for example, in the Petronas Towers in Kuala Lumpur in Malaysia, that was built about 20 years ago. You can see in between the buildings there's this sort of shock absorbing structure. And for earthquakes, for earthquake resistant structures they're building now in places like California and elsewhere, they use very tough, very ductile, but strong polymeric rubber type materials to actually sit the entire structure on. So if it starts to sway in an earthquake, which is an extreme condition because you not only have movement in the Z direction, but in the X and the Y direction too. So you have to have these kind of structures so that the building doesn't fall over. Okay. One way you can pick materials for toughness, there's something called this is called the Ashby material selection chart. And you can see here that they compare strength and toughness of materials. You really want materials that are both strong and tough for resilience, for durability. So that could be certain super alloys, titanium, actually nickel super alloys are really good at this. What's hiding back here, you see the word composites. I think this chart, I took it out of a wrong talk, and hiding behind here, there's a big area of composites. But composite materials are combinations of materials. For example, you could have a carbon fiber inside of a polymer matrix. That's a great way for making a more durable and resilient material, because essentially composites could be fibers inside of a block of material. The fibers give the material extra strength. It can be, sorry, my air conditioner just came back on. It's making a lot of noise. So if that's a problem, please send me a message and let me know. But hopefully you can still hear me. Anyway, you can form a multi-layer composite, a fibers inside of a block of other material, or particulates inside the material. Then you get kind of the best of both worlds. You can get the strength of one material combined with the flexibility of another material, or in the case of fibers in a material, fibers can actually hold the material together. So you can have short fibers or long fibers. So even in, for example, tennis rackets that are composed of carbon fiber composites, you can get this kind of strength added by having these fibers inside the material itself. So that way, when cracking occurs, what happens, the fibers tend to hold the material together. Now, you can get failure in composite materials, again, due to basically poor manufacture, a lack of adhesion between the fibers and the matrix they're in, and therefore allowing the fibers to pull out. So there's a lot of great examples of composite material that's used in critical applications, mission critical applications today. Carbon fiber reinforced polymers are very, very popular. In fact, you can even 3D print carbon fiber reinforced polymers. There's a couple companies that make machines for this. Or you can make it by laser sintering the fiber to the polymer. That's the way they're making wraps that can go around pipelines. I've seen that at work. It's very interesting watching this giant robot with a laser. Very exciting. Basically making sure the fibers are well embedded within the matrix material. There's examples of glass fiber reinforced concrete down here at the lower left, which is like fiberglass, but the fiberglass is embedded not in a polymer like the fiberglass you might use on your house siding, but embedded within concrete, and it gives it a great deal more toughness. Because when these materials have the fibers inside, the materials can flex a little bit. That's extremely important, for example, in aircraft. For example, the Boeing 787 is mostly composed of carbon laminate composites, also carbon sandwich composites. They make up the bulk of the plane now, composite materials. I know it used to be aluminum aircraft alloys, something I worked on extensively for years, but not anymore. There's a little bit of aluminum alloy, but mostly composites. Why? Well, think about it. A jumbo jet is essentially a balloon that you inflate and deflate thousands of times. So every time you inflate and deflate it, as you pressurize and depressurize it, tiny cracks, say around the windows or doors, can grow until they reach a critical crack length. So what you want to do is have a material that holds itself together, doesn't permit the cracks to grow. And that's where, for example, carbon laminate composites are extremely valuable. Okay. Sorry, I got too many slides to get through, so I'll try to jump through a few more here. One area that engineers and scientists are getting inspiration from to develop new composite materials are from natural materials. For example, armadillos. Have you ever seen an armadillo? They're armored. They have really, really tough hides. That's how they protect themselves. Things can't eat them because of the tough hide. That hide on the armadillo is actually a composite material. And if you examine it, you actually have a mixture of soft layer materials, you have fibers, and then you have a hard layer on top. This is actually being used in a certain sense now for body armor. Because if you can combine these materials, get them to adhere to each other well, that's the key. They have to adhere to each other. Then you can start to form what they call bionic composite armor. And then you can turn that into other structures as well. And they've actually the study this picture was from. They actually used aluminum and aluminum oxide as the basis of the composite, but they saw that you can have these materials with different amounts of flexibility bound together. Also, shellfish. There's been ablative armor or armor for tanks developed based on the structure of shellfish. There's an example I found recently of enhanced ballistic armor for tanks. Again, in this case, it's a bronze, aluminum, nickel, phosphorus, bronze, reinforced with very hard materials, yttria, which is yttrium oxide, and a titanium carbide nitride. Carbides and nitrides are super hard materials. So if you put little particles of those basically into the alloy, that can stop the formation of cracks, or plastic deformation, which is the physical deformation of the material. Another way that these composites can work very well is in resistance to heat. For example, we know that the old space shuttle tiles, they didn't work too good, but then eventually they made these blanket materials that went on the wings, which were a little bit more durable, but they were multi-layer composites like this that could handle the heat of reentry. And so you can take, a single carbon fiber layer might not be good enough, but if you have multiple layers with protective ceramic, for example, ceramic and titanium internal layers, that can form extreme fire-resistant materials. Even if you start to lose some of the material on the surface. So that this one study, they were looking at carbon fiber reinforced laminates that could be under load and still resist very high temperatures. So it's very exciting stuff. I've been looking at some very simple composites in my lab, not for too extreme of environment, but I'm looking at actually I've been working on making composite materials using recycled textiles. Not going to be as strong. You're not going to armor a tank with it probably, but you could use this to make a better 3D printing mechanism for printing, say, with concrete or with plaster, because you would have internal support within it that would give it that resilience that's needed, the toughness that's needed. Or you could take it and make it back into clothing. Again, I'm working with SUNY FIT, the Fashion Institute of Technology, and we're even looking at using these materials as a basis for creating catalyst nanoparticles on their surface that could be used, say, in filtration or fuel cells. So exciting stuff. What I found in my work so far is that I recycle these fibers by using a pretty green technique, just simple chemicals like sodium hydroxide, heat, and stirring, and I can separate the threads back into sort of a cotton. And then I react these with calcium sulfate hemihydrate, which is essentially gypsum, and I look at how the gypsum crystals form on the surface. And you can see here at the top picture, from an electron microscope image I took, that the fibers are indeed adhering to a lot of the crystalline material, and this makes it a bit stronger. We did some compression testing. See if I can make it work. So these are examples of some materials, not super resilient materials or super strong materials, but something I'm trying in the lab with is making plaster type materials out of gypsum, which is calcium sulfate, and combining very small amounts of recycled cotton fiber from clothing that's recycled using sodium hydroxide and some of the other methods I mentioned. So here's two examples, two nice videos my student made that'll show the force versus time, and you will see the increasing force, and then you will see it what happens as it breaks, as we're loading more and more weight onto it, in a sense. And on the left, this one I'm running now, you can see the blue line moving, hopefully. That shows the force being applied to it. And what you can see at the bottom, as the force slowly increases, you'll see material falling off, flaking off around the structure. So pure gypsum plaster is pretty brittle. It's basically, it starts to fall apart pretty readily. And we stopped it after it just started falling apart, but you can also already see a large amount of material around the bottom. Then if we try the material that has 0.5% weight percent of cotton in it, you'll see that you'll see a similar shape to the curve, but as it breaks, you'll see the material doesn't fall away. It stays more or less connected until if we kept going, it would go a lot further. But you can't tell too much from the curve at the top, except for the fact that it's still supporting a significant amount of force. The amount of force it can hold, or the amount of weight it could hold, doesn't fall off as rapidly either. So hopefully that's an example that can demonstrate the value of having fibers in something as simple as a plaster. You can also make polymers more robust. For example, you can cross this. A study just came out on cross-linking certain polymer networks, supramolecular polymer networks, using something called metallocycles, which are just basically metals embedded in, usually things like silver or platinum or bismuth, into a polymeric structure, and then using these as cross-linkers. Again, not a new technology at all, because if you think about it, in 1839, the process of vulcanization was developed by Charles Goodyear. In that case, they were cross-linking polymers, in this case with sulfur. That without that, you wouldn't have basically had today's car tires, because the material wasn't durable enough. It wasn't resilient enough to be a car tire. So you had to find a way to cross-link these materials together. Modern tires also add materials like this to limit or retard oxidation. A lot of these materials, these resilient composites, are being used, for example, in thermal insulation, as I mentioned. One material that's very exciting, which we don't have much time to talk about, are aerogels. Aerogels are basically materials that are formed that have a sponge-like structure. Sometimes they can be formed with nanofibers, with freeze drying techniques. I've seen them formed with supercritical carbon dioxide. These form structures that are flexible. They have a property called superelasticity, which means you can change their dimensions a lot without them breaking, and they're also ultra light. So you can make certain types of nanogels or hydrogels that can solve a lot of these problems. So before I completely run out of time, I just want to say a little bit about other failure mechanisms like weathering and chemical degradation. There's lots of forms of corrosion. I studied corrosion. Corrosion was the basis of my PhD work. I was looking at high nitrogen alloys and how they resisted extreme environments, including 4 molar hydrochloric acid. And basically, there's lots of types. We're not going to talk about them. There's types of corrosion like uniform that attacks the entire surface, pitting that attacks small areas depending on contaminants or defects in the material. We mentioned stress corrosion cracking, crevice corrosion that occurs where you have an occluded area. That leads to a lot of failures. There's even a type of corrosion, which you may or may not be familiar with, called microbially influenced corrosion, which includes both the biofilm that bacteria form when they live on a surface, even a metal surface. This biofilm allows crevicing type corrosion underneath, because you have the formation of something called oxygen cells, where you have 2 different levels of oxygen in the area, and that forms an electrochemical process. Or the bacteria themselves, by just what they do, how they eat, actually will create an environment that's that promotes corrosion. And in fact, certain types of sulfate reducing bacteria, which you find in oil pipelines, can even eat some of the passive film, the protective film that forms on stainless steel. So we think about resistance to corrosion. Probably one of the more exciting areas that have been developed recently are nickel-based superalloys like Hastelloy, and new ones being developed. These are good in very high temperature environments, because high temperature corrosion or oxidation is obviously something that forms under extreme conditions. And so these high temperature, these high nickel-based alloys, these nickel-based superalloys, can prevent both electrochemical corrosion by helping to form a very durable passive layer or oxide layer on the surface, and also can help prevent high temperature oxygen corrosion by forming a layer on the surface that prevents the fusion of oxygen into the material while it's heating, limiting the thickness of the oxide layer that forms. That's why you can use it in turbine blades and areas like that. A lot of materials in superalloys do protect against corrosion, or they do other things. For example, chromium, molybdenum, palladium, these metals are added to improve the thin layer, passive layer that forms on the surface that's protective. Nitrogen actually forms very thin nitride layers. So I'm not going to go into this because of time, but the thin layer that's only about 3 nanometers thick. That's why, by the way, the reason stainless steel looks shiny is it's covered with oxide, but the oxide's so thin that you can see through it. It's only about 3 nanometers thick. And in that layer, you form a chromium and molybdenum rich layer, for example, in certain stainless steels, that actually acts as a rectifier circuit to prevent things like chlorides and hydroxides from reacting with metal ions and causing rust. All right. You can also form much thicker surface nitrides and surface carbides. These are very, very hard, very protective layers. And so a lot of work being done today is looking at using, for example, as you see here, plasma nitriding of materials to make them, again, more resilient, more robust, and more able to resist attack of various types. We have groups here at Stony Brook, for example, the Thermal Spray Lab, that uses a process called thermal spray, which you may or may not know about, which involves using a high temperature source, using basically a combustible gas gun, where you pour powder into the gun, and that powder actually melts and then splats. They call it splatting against the surface, forming a very resilient, a very strong, say, for example, a ceramic layer, like an oxide or a carbide layer. They can even do thermal spray onto polymers and even onto paper. I've seen them do it on cardboard. And it works. So it's a really exciting process that we're working on here. There's other types of coatings, maybe not as advanced in some cases, but for example, chemically agent resistant or CART coatings that are used in a lot of defense applications. These are multi-layer paint coatings, basically really, really good paints. Sherwin-Williams and other companies have made these paints. They use a pre-treatment layer to help prevent corrosion, and an epoxy primer that helps the layers stick together and also helps prevent corrosion, and then a top coat, which is chemically resistant, usually a polyurethane enamel that contains, this is the structure of polyurethane. And these nitrogen groups in here are actually very good at both reacting to prevent chemical attack, but also helping you paint the surface, say, with materials for camouflage. I'm not going to get too much into this because we're almost out of time. Responsive materials are another class, in its sense, of materials that can absorb energy via dimensional or chemical change. Like, for example, this is work that was just published recently at Lawrence Livermore National Lab on what are called polycatenated architected materials. These are materials that almost look like medieval chainmail, getting back to medieval stuff, but when the temperature changes or there's a change in humidity or something else happens, the structure actually either expands, contracts, it can move. These are sometimes called 4D materials because they're 3D materials that have that fourth dimension of time, and they may actually stand up or do something else based on this. So they're used in robotics and actuators, but they can also be used to absorb energy and give you protective surfaces. I'm currently working with professors in the civil engineering program to look at using materials that can change their shape to respond to high temperatures. And so that's work that's just starting out. Also, I did not want to end up without at least mentioning self-healing coatings. These are coatings that act like your skin does. When they're broken, when they're cut, when they break, healing agents can move into the cut and reseal them. Very important in paints. And for example, you can put corrosion inhibitors in little nano or micro capsules that are released if there's a scratch. So these can be corrosion inhibitors like sodium molybdate, ceria, various organics, even linseed oil, epoxies that get released when you get a crack or a cut or a scratch. These healing mechanisms can also be activated by pH changes when it gets very acidic in the environment, under light conditions, heat, moisture. All these can help activate the healing compounds. I saw an example of this recently published just a few months ago, I think, actually, maybe a little longer than that. This was a material, a polymeric self-healing material developed in the UK for self-sealing of fuel tanks that have been subjected to damage, say an attack, and the fuel tank is punctured. And what they do is they create an elastomeric paint type system that, if penetrated, can reseal itself. And they showed that here. It's a multi-layer system, and when it's penetrated, the elastomeric material that's combined with the polyurethane cork type coating can actually reseal it. So at least you may still have to get it repaired, but you can get the truck or the tank or whatever back to a depot in time, and it doesn't just die out in the field. So I pretty much I have some other slides I can show. I pretty much covered it all. So I can give you a quick. There's a very high level summary, but the key to developing resilient materials in extreme conditions and not so extreme conditions is understanding the failure mechanisms so that you can understand the threat multipliers that lead to the failure. Understand resilient materials, how they respond to their environment by essentially absorbing the threat. They absorb energy, they can convert energy to useful chemical or structural changes, or just respond to the damage in the environment by exposing by creating a chemical layer that protects it further. And so new materials and material systems are being developed all the time, requires a strong and healthy research enterprise, which I always promote, and a collaboration between universities, industries, and the military, for example, and also national labs. All have a role to play and all can develop these materials because they have the analytical tools and the processing capability. So if you have any additional questions other than what I can answer right now, please feel free to email me. I'm more than happy to chat about stuff. Okay.
Hey, thanks, Gary. That was a great presentation. We got questions coming in. Remember, you can type your questions into the Q&A box and on your Zoom screen. Let me just start going through them. It's kind of rapid fire because there's a few here, Gary.
Okay.
It seems like composite materials also create some kind of performance trade-offs that you mentioned. Are there any general environments or situations where composite materials tend to perform poorly that might matter for the military?
Yeah, I think you just have to look at the sad little Titan mini sub that imploded on the ocean floor a couple of years, just 2 years ago now, the one they were using to explore the Titanic. And that was a composite hull that failed under extreme conditions. Problem with composites, they're really, really good under tension, not so good under compression. And so they had a situation where they had a mixture of tensile and compressive forces, then they were not designed well. The thing about composite materials is they're often they're isotropic. They often have different properties in different directions, right? So if you have fibers going this way, the properties to the side or along the length are going to be different. So you have to realize that. So it's more of a design challenge to make sure that the CAD software, the design system used, understands the nature of the material and what will help. I don't know if that answers that.
So, is it necessarily true that resilient materials will cost more upfront and be harder to maintain, especially on the field in deployed situations, even in combat environments?
Good question. I don't know exactly, but I would think easier to maintain because they're less likely to fail, and be more durable. They also may be able to be folded or moved more easily. They tend to be lighter in weight, which is a good thing. So even though the material itself might cost more, you might save fuel. That's been the case of aircraft. And so you're saving money somewhere else in the process. But as far as, yeah, they could be more expensive the same way that, a 3D printed stainless steel is more expensive than stainless steel that's, from a blast furnace that you then, machine. However, by having the ability to print, you have the ability to make wild structures. So I think the answer to that is yes, it can be more expensive. It depends on the composite, but I think it will be more durable, and it also will give other benefits.
A lot of this in defense, the use of materials turns into a cat and mouse game between the threat and the person trying to protect themselves. So, if you understand failure mechanisms, I bet you can also give advice to people trying to make materials fail. So the question is about directed energy weapons, high energy lasers and microwaves.
Mhm.
Do you have any thoughts on how these systems can be designed to encourage the failure of materials?
That sounds like good fun. I'd like to try. Uh, just send it all over to me. Let me play with it. I'll make it work. As far as making this is a really actually all joking aside, it's a really good question because one of the things that I have spent a lot of time doing are building setups for accelerated corrosion testing. And you have to, in order to make it relevant to the real world condition, you have to be very careful about design again. And so for directed energy weapons, other than using the weapon, as is, basically what you expect the energy to be from the weapon, and the type of energy and the duration and so forth, and then just basically setting it up and firing at things. Other types of accelerated tests that can be done that are simpler, maybe less expensive, would just be testing under high temperature. Thermal shock. A lot of directed energy is about thermal shock, right? So you're basically heating it up extremely rapidly. You can do that with conventional systems. Maybe not as rapidly, but you could have, you could design a furnace that can heat the material up as quickly as possible, and maybe even change the temperature rapidly by moving it from hot to cold environments, trying to replicate thermal shock. And of course, obviously, computational modeling is critical. There are really, really good computational modeling systems now that allow you to add different stressors into the system to see what will happen. So you can build an atomic scale model or even a macro scale model of the material, try to have it cooperate with the physics of the material we normally have, and then look at how the effect of different energetic impingement on that would be.
Uh, Question on if your company or an inventor has already developed materials, what are your thoughts on the process by which you get to the point of implementation, further manufacturing, and then actual use by either military or commercial applications?
Sure. I mean, I'm not an expert in that, but qualification of materials is critical. The I remember that, being at a number of meetings where we were discussing things with DoD and other folks, and there was that what they called the valley of death between the material synthesis and research end of things, and the actual application in the field, and the ramp up, the scale up of developing the materials. Scaling up is a very, very important issue. I can make little tiny amounts of material in the lab of almost anything you can imagine. We can try to put it together. The people working on fusion downstairs, materials for fusion, not fusion itself. They use spark sintering and other techniques, and they make little tiny pellets of material that could be tested. Turning that into something that you would coat the inside of a reactor with is a very, very different world. So yeah, I think the need for scale up is really important, and that's where joint research between, say, universities, national labs, industry, and end users and DoD are really important because the scale up can be developed through that process.
We'll do one more question, or maybe two. What do you think are the best resilient materials for larger military structures? Are there any things that you would see are more resilient than concrete or steel without just driving up costs beyond belief? What do you think is promising there?
Well, I mean, there's a lot of stuff being worked on. In fact, I was talking to some researchers over at Delft, which is a university in the Netherlands. And they have a big issue with, they obviously build large scale wind turbines, and they have an issue of wanting to make sure those things are durable when they're out in the water. And so they've been developing large sheets of material that can be basically wrapped completely around, you know, the whole turbine stanchion system. These are flexible fiber containing cloths. And basically they just have to make sure they adhere well to the surface. Now they have challenges with that too, because anytime you have dissimilar materials in contact with each other, you could have gaps, you could have voids, you have places where damage could occur because you could get trapped, you know, trapped water or something in there. So it's really important to look at these adhesion issues. So I say surface coating is probably going to be the most cost effective, where you can't just build the whole thing out of a robust material. So I think the more exciting work is being done in the coatings area, like thermal spray, which you could do on large scale structures. In fact, they built a thermal spray system here at Stony Brook some years back that was actually being used to crawl up and down the outside of the Golden Gate Bridge, to actually test the idea of coating the surface with something that wouldn't have to be painted very often, you know, an oxide coating. So yeah, you can, I would think those types of materials also, you know, you can also change something in the processing of metals that helps make them a little more durable through heat treatment. So that's actually treating the metal after it's formed, and that might also be very helpful.
All right, Gary, we're out of time. So the question on the best dragon fire to use on Valerian steel, you'll have to take that for next time.
I will.
Okay. So with that, Gary, thanks for the great presentation. And I want to thank all of our attendees for joining us today and for all the great questions. We're going to post this recording online, hopefully including those videos and the slides as soon as possible. If you have feedback about this event, especially topics you'd like to see us cover in the future, please email us at eti@ndia.org. I want to take the opportunity to highlight a few ETI upcoming events. Our next Tech 101 is going to be on wearable technologies. It's on July 23rd at 1 p.m. Visit NDIA's calendar events to stay up to date for the next 101. Additionally, ETI has some great upcoming webinars in July. How to steal AI algorithms at the edge and protect them, in partnership with Mercury Systems. That's on July 15th, 2025. Second one is Become a Technology Apostle. How to successfully discover, nurture, and implement emerging technologies. We're doing that one in partnership with Parallax Advanced Research. That's on July 18th. Be on the lookout on NDIA's calendar events for more information on all these events. The Emerging Technologies for Defense Conference is coming up at the end of August. August 27th through 29th. Visit ndiatechexpo.org for information. I want to announce that we've got Undersecretary for Research and Engineering Emil Michael and Undersecretary for Acquisition and Sustainment Michael Duffey, both confirmed, as well as a growing number of government, industry, and uniform military speakers, plus opportunities to exhibit, sponsor, and present for NDI members. Again, for all of that information, go to ndiatechexpo.org or scan the QR code on the screen for more information and to register. Thanks once again, Gary, for joining us today, and thanks to everyone else for joining Tech 101.